Hi, Cole.
Hello.
How are you doing today?
I'm doing pretty good.
I have a geometry student in an hour that just sent me 3 documents. And tell me whether this is going to help you or not. Is this what you have sent
This
me?
is what we're doing.
What's that?
This is what we're doing, yeah.
Okay. Shall we just use her material here?
Mm-hmm.
All right, let's find the first one. That's 10. Must be the bottom one here. Oh, no. Looks like the ones begin right here. All right. All of these word problems in geometry result in right triangles, especially the ones involving shadows. Because shadows are almost always given off by things that stick up from the ground at a right angle.
Okay.
Okay? Now, in this thing, they're saying here's a cliff at a right angle, and the cliff casts a shadow. In other words, the sun's coming from that direction. So, cliff casts a shadow where this is 304 feet, the base of that triangle.
All right.
If a 3'9" child walks along the shadow of the cliff, in other words, he's starting here and he's walking along in that direction, for 178 feet until the tip of his shadow just overlaps the tip of the cliff's shadow, determine the height of the cliff. So what they're saying is the boy's going to walk until his shadow, the tip of it, is the same point as that. Okay? And this boy we know to be 3 feet 9 inches tall. So, what do we know about this big triangle and this little triangle? In other words, this is the little triangle.
They're similar.
Okay. So what ratios can you say have to exist? Well, let's see. I didn't. This is 178. In other words, he walks along that shadow for 178 feet. And we want to figure out x. So 178 feet is the distance from there to there. 304 feet is the distance from there to there. So give me a ratio that applies to these two similar triangles. X is to what?
Sorry, what? X is the height.
X is to what? Whenever you're dealing with similar triangles, you're going to end up with ratios. So X is to 3 foot 9 inches, which is 3.75 feet. That's the ratio of that side to that side. What does that equal to?
304 to 178.
Really careful. 304 is correct.
Yeah. 304 minus 178.
126. In other words, this distance right there is 126.
Okay.
So I can say x is to the height of that triangle as the base of that triangle, which is 304, is to the base of that triangle, which is 126. And that allows us to solve for x. Now, how do you solve that? What's the best thing to do to solve that equation?
Cross multiply, so you have 126x
Before you automatically cross multiply, notice that there is a step that's one step shorter than that. If I cross multiply, then I end up with this, correct? Now what's the next step?
multiply 3.75 by 304.
By 126. We're going to divide both sides by 126. We're trying to isolate x, right?
Yeah.
Okay, well that was two steps. Now notice that if I begin the problem without cross multiplying, but merely multiplying both sides by 3.75, I have my answer in one step. So just because you can cross multiply doesn't mean you should. If your variable is in the numerator, usually you should not. Usually it's a one-step solution. Because all I have to do to get rid of this denominator is to multiply both sides by 3.75. I don't need to cross multiply and then have a second step where I have to divide both sides by 126. You see the difference?
Mm-hmm.
All right. And I don't know, given that we're only doing half-hour sessions, I'm going to leave you to come up with that number. The number is not important, it's the formula that matters. You know what I'm saying?
Mm-hmm.
All right, oh no. Is there a second one here or not? Is 11 on this? Let's do 11, even if it isn't. In other words, what you're dealing with here are ratios. If they have 37 wins and 22 losses, and they continue at that same rate, how many wins will they have at the end of the 82-game season? And let's set up a ratio.
Okay, so I know it's a very small project, but...
In other words, I think you could probably figure this out given enough time, but you might do it in a manner that's not the most efficient. You might not do it as a ratio. What I want is the number of wins in an 82-game season.
Oh, so 37 over 82 equals 22 over 82?
Well, 37 is how many wins they have at the moment. How many games have they played at the moment?
Sorry, what? Oh, they've only played 59 games.
Okay, so there's your ratio. In other words, this is their win ratio right there. And we want it to be the same as their win ratio at the end of 82 games. And again, we don't want to cross multiply. W is just equal to 82 times that ratio of 37 over 59. And of course, how you simplify that is another matter, but
Izzy, thank you no more.
This is a straight ratio. And notice that if we do 37 to 22, if we make that mistake, that really makes it more difficult. Because now we have wins over losses, and we don't know how many losses they're going to be. So I guess my losses would have to be 80, my wins are 82 minus my wins, right?
Mm-hmm.
So I could do it like that. I still have one equation, only one variable. I'm going to be able to solve for W. It's going to give me the same answer. But notice the algebra is a whole lot harder.
Mm-hmm.
To solve this, I really would have to cross multiply, and then I would have to gather all my W's on one side, all my numbers on the other. It would be quite an algebra problem. So setting up the ratio correctly in the first place makes the algebra a lot easier. In other words, setting it up as wins per total games, in other words, 37 to 59, well, we know what total games is. It's 82. So that's the far better way to do it.
Mm-hmm.
All right, let's go to this page. Am I missing anything here? Oh, okay. There is a particularly neat thing that happens that they must have taught you about. Otherwise, I don't think we'd be looking at this triangle. If you take a right triangle, any right triangle, and you drop a vertical from the vertex that contains the right angle to the other side, like that, so that that's also a right angle, turns out two very interesting things happen. This triangle is similar to that triangle, and both of them are similar to the large triangle. In other words, we end up with three similar triangles. And that's exactly what's happened here, is they've started with a right triangle. They have dropped a vertical from the vertex where the right angle is to the opposite side, making a right angle. That means that triangle is similar to the big triangle, that triangle is similar to the big triangle, and they're both similar to each other. Now, the only difficulty here is orienting it. In other words, when you are looking at similar triangles that aren't oriented the same way, it can be a little difficult. So, what's the biggest angle other than the right angle here?
Oh, this one with this problem, today my teacher said that there was not enough information to solve this problem, therefore we did not need to do it.
Okay, I think she's wrong, but
Just
let's just, I've only another minute and I will explain this a little bit. Which angle is bigger, this one or this
the one by x.
Correct. Because it's opposite the biggest side that's not the hypotenuse. Okay, so I'm going to label that angle A. I'm going to label that angle B. So I know A and B are complementary, but A is bigger than B. Okay. So now when I look at each triangle, I know that this one of the angles is bigger than the other one. Now that I think about it, she's right. She didn't give you all the information you need to solve this. But that first piece of information that I gave you is critical. You create three similar triangles when you do this thing. And given enough information, you can solve it. Just using similar triangle ratios. Is all you have to do is figure out how to orient these things so that they're the same. Well, clearly this triangle is not similar to this triangle because this angle is equal to that angle. That's not true, right? We just proved that this angle is bigger than that angle. So this can only be similar to this if this angle right there is the one that's equal to that angle right there. And this angle right there is equal to this angle here. So that helps us orient them. And then that actually tells us the similarity ratio. 32 is to 24 is the similarity ratio. In other words, both of these right angles have hypotenuses that are proportional to one another. In other words, we get our similarity ratio from 32 over 24. The problem is that she didn't give us any other measurement. She didn't give us an X or a Y or a Z. So we can't go any further than concluding that the similarity ratio is 32 to 24. Because those are the hypotenuses of both of these two triangles.
Mhm.
Which one here? We only have a few minutes. Let's do 26.
All right.
It looks like either one of them is going to test us on the same principle. The principle being that if you have similar figures, the ratio of their areas is the square of the ratio of their linear ratios, and the ratio of the volume is the cube of their linear ratios.
Mm-hmm.
So they're telling us the surface areas of these two pyramids have a ratio of 121 to 4, big pyramid to little pyramid. That is the area ratio. What's the linear ratio?
11 over 2.
What's the volume ratio?
I don't remember what 11 is. It's something over 8.
11 cubed over 2 cubed. In other words, the volume ratio is the linear ratio cubed. Okay? Now, in this particular problem, we don't actually need the volume ratio. I just introduced it just to make sure you knew what it was. Because what we have here is he's calculating a vertical height of the smaller pyramid to be 24 feet. What's the vertical height of the larger pyramid? When we're talking vertical height, are we talking linear ratio, area ratio, or volume ratio?
Linear ratio.
Correct, because it's measured in feet. It's not measured in square feet. And it's not measured in cubic feet. So all you have to do is look to the units to know what ratio they're giving you.
All right.
Well, we know the linear ratio is 11 to 2. Smaller pyramid is 24 feet high. How high is the bigger pyramid?
It's indeterminate, so X.
Well, it's 11
Oh.
halves that height. In other words, 24 feet is to X, which is the smaller pyramid's height is the bigger pyramid's height, as the smaller pyramid's linear measurement is to the bigger pyramid.
Okay.
And all of these problems, it's very important to understand whether you're going small to big or big to small. Now, I know there's at least one teacher at Chatfield that likes going small to big. And I personally think that's a big mistake. I like going big to small. The reason is when you go big to small, you're always dealing with numbers greater than 1. When you go small to big, you're always dealing with numbers less than 1. And when you start taking cube roots and square roots of numbers less than 1, it can confuse someone. Whereas if you take square roots and cube roots of numbers bigger than 1, it makes much more sense. So, in other words, x here would be, here I would want to cross multiply. It would be 11 times 24 divided by 2. In other words, this ratio you set up was incorrect because you were comparing the area ratio.
That's not me.
Oh, this compares the area ratio to the linear ratio. And you have to make sure that you're writing a ratio equation that compares the same thing. In other words, it's very important to know here that the linear ratio is the square root of the area ratio. So it's 11 to 2. That's the ratio we should be dealing with. In other words, the big pyramid is 11 halves bigger in vertical height than the smaller pyramid because of this ratio.
All right.
All right, Cole. I will talk to you next Monday.
Talk to you next Monday.
All right. Bye-bye.